Hello and welcome. This is the Taming Wild AI channel, where we bring AI technologies out of the wild using the best practices of software engineering. In the last two episodes, we started taming the author's implementation of efficient neural architecture search. The implementation has four execution scripts. CFAR10 macrosearch.sh performs macro search over convolutional networks of a specified depth. It searches through layer types and connectivity configurations for a network that performs well on the CFAR10 classification task. CFAR10 macrofinal.sh trains from scratch a network that was found from macro search. The script successfully trained a 24-layer network to 93% accuracy. But when we took an actual output of the previous script and gave it to this one, we ran into some errors suggesting incomplete code. CFAR10 microsearch.sh performs microsearch over small convolutional and reduction cells. It also searches through layer types and connectivity configurations, but the cells it generates are repeated and then connected together to form a network that performs well on the CFAR10 classification task. CFAR10 microfinal.sh trains from scratch a network whose convolution and reduction cells were found from microsearch. The script successfully trained a network defined by the previous script to 93% accuracy. We now have enough unit and integration tests to confidently make improvements to the code without breaking anything that is working. We already isolated the dependencies on TensorFlow in a single file, framework.py. We also removed unnecessary introductions of temporary variables. Another area that could use improvement is configuration management. Right now, the hyperparameters and other configuration information is captured in command line arguments. As the README says, all hyperparameters are specified in the scripts that we describe below. It's great to have these in one place, but let's see what happens to those command line parameters. We've made fw.run an alias for tf.compat.v1.app.run. There's not much documentation on this, but if we look at the source, we see that it calls absol.app.run. If we now look at the documentation for absol.app.run, it says that it parses the flags, printing a usage message and failing if illegal flags or flag values are specified. By flags, they mean command line parameters. Before run is called, in this case when the file is loaded, the expected flags are specified. Any other command line parameters passed at runtime become available as an argument to main. It's not clear to me why this example introduces a global variable flags. It could simply have been declared inside the main function where it is used. In any case, I definitely appreciate support for specifying and then parsing command line arguments. Accordingly, at the top of main.py are specifications of the expected command line arguments. In this case, any other command line parameters passed at runtime are silently ignored. Some flags are used in main. Main calls train, which uses some flags. Train calls getOps, which passes a large number of flags into the constructor of the child or the controller. It's confusing because most but not all of the flags prefixed with child are passed to the child constructor, and most but not all of the flags prefixed with controller are passed to the controller constructor. Now, if you look at how the flags are expected to be used, the documentation says rather than an application having to define all flags in or near main, each Python module defines flags that are useful to it. This behavior is implemented by having all modules share a common global registry object containing all the flag information. So they foresaw the need for multiple modules to access configuration information. Their solution was very reasonable. Modules that need flags should specify them and then access them by importing the flags variable. But the solution in our code is to pass a large number of flags into the constructor. Let's change our code to be more in line with how flags are expected to be used.
Let the code flow.
And all tests are passing except the ones known to fail. So far, I've made changes for macro child and micro child. Let's review what I did. In main.py, I made flags a local variable in each function. This is generally a good idea because when a function has fewer dependencies on the global namespace, it's more reusable elsewhere. I cut a bunch of define statements from here. Like the documentation said, I pasted them in the modules that actually depend on those flags. In getOps, I stopped passing all of the flags as constructor parameters. In macrochild.py, I added define statements for the flags that the macrochild class depends on. It turned out that many of the flags that were being passed to the macrochild init method were simply being passed on to the superclass init method. I stopped passing all of those flags. The init method now initializes member variables from a local flags variable. Very similar changes in microchild.py. New define statements for the flags that the microchild class depends on. Stopped forwarding flags onto the superclass init method. And the init method now initializes member variables from a local flags variable. Models.py contains the model class, which is a superclass of both macrochild and microchild. As you can see, many of the flags are defined here because both classes depend on them. The init method no longer takes them as parameters. Instead, it initializes member variables from a local flags variable. We can't forget the changes to the tests. In the unit test file for main.py, I stopped referring to flags as a global variable. These are the unit tests for macrochild.py. Now, before these changes, member variables were getting initialized from default values of parameters of the init method. After these changes, they're getting initialized from default values of command line flags, which might be different. So I had to add several lines to this mock to initialize those values the way my tests were expecting. Similar changes in the tests for microchild. I had to add several lines to this mock to initialize the values the way my tests were expecting. I also had to add a new mock used to test an invalid value for the data type flag. Again, I removed parameters from all of my instantiations of microchild. Just one change in the tests for the model class. Remember that the init method initializes the data format member variable from flags. For this test, I had to set the flags data format before instantiating the class. Now I'll make similar changes for macrocontroller and microcontroller. Alright, I've made similar changes for macrocontroller and microcontroller. In main.py, I cut many command line flag definitions. Some of them I pasted in other modules that do depend on them. Others were completely unused. The remaining ones are used in this same module. GetOps was passing several flags to the controller constructor. I removed those. Controller is the superclass for macrocontroller and microcontroller. It originally was written as an abstract base class, but I decided to follow the same pattern as I did with the child classes and collect common member variables here. They're initialized from command line flags defined at the top of the file. In macrocontroller.py, I defined the command line flags that the class depends on, added a call to the superclass init method, and initialized member variables from the flags. In microcontroller.py, very similar. I defined the command line flag that the class depends on, added a call to the superclass init method, and initialized member variables from the flags. It was inconsistent to have the superclass of macrocontroller and microcontroller be called controller and have the superclass of macrochild and microchild be called model. So I renamed it to child. This, of course, required small changes to macrochild and microchild, as well as the corresponding tests. When I renamed model as child, I started seeing a lot of test errors. The tests would pass in isolation but fail when all run together. Apparently, renaming the class caused the tests to be run in a different order. It exposed a hidden dependency between the tests. I traced this down to the fact that the tests were using the global default graph object in TensorFlow. I added context managers to create new graph objects during the tests. These tests have cleaned up the instantiation of child and controller classes for micro and macro search. The downside is I did increase coupling between those classes and command line flags. My rationale is that this is an expected use of TensorFlow command line flags. Also, the coupling to flags was really always there. It's just that previously it was indirect through the init methods and main.py. Now it is more direct. One thing that bothered me about the code was the repeated checks of the data format. You can see almost 50 checks like this throughout the code. One reason it bothered me is that there is a bug in the code related to it. Here the author meant to check for NHWC but mistyped it as NWHC. Another reason it bothered me is because the result of the check is handled inconsistently. In some cases, the code throws an exception for an invalid data format. In other cases, it simply assumes the other format. And in other cases, it does nothing if the format is invalid. Another reason it bothered me is because the data format is actually passed in as a command line parameter. So there's no reason to be checking it dynamically during execution. The main reason it bothered me is every check created two different paths through the code, and I had to write a separate test for it. Instead of storing a string representing the data format, I would prefer to store an object constructed closer to the beginning of execution. The choice of object will depend on the data format, and once chosen, the object will implement these methods as necessary. Let's make this idea a reality.
Let the code flow.
Alright, so I've created this data format class and I've put it in child.py because all of these checks of data format are either in child.py or macrochild.py or microchild.py. There are a few in imageops.py, but we'll deal with them later. What I've done here is created a data format class and two embedded classes inside data format, one for the NCHW format and one for the NHWC format. Now I want the data format class to be a factory for objects that will handle those data formats appropriately. I don't want anyone to call the init function on it, so I'm raising an exception if the init method is called. What I did do is add a static method, a kind of factory method called new. And you'll pass this a format string, and based on the format string, it will return either an instance of NCHW or NHWC. Now, if you provide an invalid format, then this will give you a key error right away. So that's going to allow me to handle invalid format specifications consistently. Now I'll initialize the member variable data format to be an instance of this object based on the data format specified in the command line parameters. Now I'll go through all of these checks and replace them with calls to methods on the data format object. I wasn't sure what to call this method, so I gave it a name based on the method that it's being called from. Now, if it's the NCHW format, then I want to perform the actual TensorFlow transpose. And if it's the NHWC format, I want it to do nothing, so return the input. Similar here for this other check. This is actually performing the same operation as before. So I'll just reuse that method that I already wrote. And that was also using the same method that was being called before. All right, so that takes care of all of the checks that were in child.py. Now I'll go through the rest of the checks and replace them. Let's review the changes I made. In the NHWC and NCHW classes, I added a name attribute. Because some of the TensorFlow calls want you to pass one of these strings. The code also passed channels first or channels last to TensorFlow in one place. So I added this as an attribute as well. I actually think this is a defect in the original code because TensorFlow expects either NCHW or NHWC, but it's also possible there's some backward compatibility in TensorFlow that allows these other values. I made each of these methods static because they don't use any data stored in the object. Each of these methods has a different implementation in the NCHW or NHWC class. At runtime, the code just calls the method on self.dataFormat. The choice of which implementation gets called is made when self.dataFormat is first instantiated. This is an example of replacing if statements with polymorphism, and it's a powerful way to make your code cleaner and easier to understand. If you recall, there were a few data format checks in imageops.py. I took one of the functions, global average pool, and simply made it a method of the data format classes. Another function now accepts a data format object as an argument and then calls the getC method on it. I did modify my tests as well to accommodate the use of the data format classes. If you remember, I had marked one of those tests known to fail because it was exposing the typographical error in the code. After these changes, that code was able to make progress, but I did have to modify my test to cover its full execution. I finished the test with mocks and patches just as before, and then removed the known to fail designation. Now there are only 2 tests remaining with that designation. The rest of my unit and integration tests continue to pass, and code coverage remains at 96%. It turned out that another one of my tests that was known to fail started making progress after these changes. I modified the test to cover its full execution, and it's now passing. I made several more changes to replace if statements with polymorphism. I introduced clip mode, optimizer, and learning rate classes. Each of these is a factory for a set of embedded classes, and each embedded class implements the same method in a different way. Unlike data format, these are actually storing values of various flags very close to the code where they're actually used. This is a practice that makes debugging a lot easier. After dealing with flags so much, I decided to fix the last test that was known to fail. This was exposing a reference to flags.numAggregate even though that flag was never defined. I changed it to refer to flags.childNumAggregate and got the test passing. All my integration tests are still passing. All my unit tests are passing. And code coverage is actually up to 97%. Now I added almost 200 lines of code. And I actually removed a couple of tests because they covered code that no longer exists. So you may be wondering how my code coverage has actually increased. The answer is that I never patched or mocked any of the classes that I introduced. The code paths that the tests were covering just happened to go through these new classes now. And the tests that were known to fail are now progressing through additional lines of code. In this episode, we made improvements to configuration management in the code. By initializing member variables directly from flags defined in the same module, we got our code to behave more like the flag management infrastructure expects. We were able to remove global variables to promote portability of functions, and we reduced the passing around of large numbers of command line flags. We collected some of the command line flags in new classes of objects and moved the code that depends on those flags into the objects. This replaced several runtime condition checks with polymorphism, and it will make debugging easier. Our changes fixed a couple of known test failures, and we completed those tests to cover additional code paths. The changes also suggested a fix to a final known test failure. Now all tests are passing and code coverage has increased to 97%. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might as well. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.